Okay, so what type of candidate accept which offers? Um, well, we would need the wage they get at Warwick to be greater than equal to what they would get if they get some other job. Okay. Suppose there's only one type, and that type is strictly positive. Find the unique subgame perfect Nash equilibrium. Okay, so what is Warwick going to do in any subgame perfect Nash equilibrium? Um, well, the candidate accepts so long as wage is greater than equal to alpha times theta. So Warwick will offer a wage is equal to alpha times theta. As far as the candidate is concerned, the candidate will accept if their type times alpha is less than equal to W. Okay, so this set of strategies constitutes the unique SPNE. Okay, suppose we now have two types. Find all PPEs. Well, we know that it's always optimal for Warwick to offer a wage equal to alpha times the type, but of course now this can be either the low type or the high type. So right, so that means Warwick will either offer alpha times theta 1, or Warwick offers uh, alpha times theta 2. These are the set of its optimal actions, and which which action it actually undertakes um, depends on the prior distribution over types. So say that the probability that a candidate is type 1 is some q, where q is obviously between 0 and 1. That means that work expected utility from offering a wage equal to alpha theta 1 is going to be probability that the candidate is of a low type times theta 1 subtract, which is just Warwick's payoff, right? The type of the candidate subtract the wage that's paid, plus 1 minus q, that is the probability that the candidate is a high type. But of course, the high type candidate will not accept this wage, so Warwick's payoff would just be 0. Warwick's expected utility from offering a wage equal to alpha theta 2 is going to be the probability that the candidate is a low type times Warwick's payoff, plus the probability that the candidate is a high type times Warwick's payoff. Okay, and so basically, whether Warwick offers alpha theta 1 or alpha theta 2 depends on the parameter q. So if which then Warwick will offer then well no. Then the optimal wage for work to offer is alpha theta 1, and it turns out if we do a bit of algebra, this will be the case when q is greater than okay. However, if we have the converse situation, then the optimal wage is, and this is the case when q is less than now if q is equal to this expression, then Warwick is indifferent between the two wage offerings and will simply mix over with some probability 0, 1. Okay. Okay. Suppose again, okay, so in this situation where we have Warwick can now offer a test to the candidate. The low type succeeds the test with the probability p and fails the test with probability 1 minus p, and the high type candidate always succeeds at the test. So we're asked first, under what conditions does Warwick administer the test? And if Warwick does administer the test, what does it offer following each of the two possible test outcomes? Well, the first thing to notice, so we'll answer, right, so the first question is dependent upon answer to the second, right? Because Warwick's expected utility from offering the test will depend on what it offers after each test outcome, and so we have to answer the second part first. The key thing to notice here is that the test is being used as a screening device. So its purpose is to try and help Warwick identify the type of any given candidate. So this means that the test must be able to discriminate between candidates. So in any equilibrium outcome, the test must be playing this screening role. So after a failure, right, if the candidate fails, then of course Warwick will offer alpha theta 1 because only the high type will never fail, so that means that the candidate must be of a low type. After success, what will happen, right? In any equilibrium, after success, what must Warwick offer? Well, if in any equilibrium they're going to be offering in any equilibrium whether administering the test they offer alpha theta 1 after a failure, then in order for this to be an equilibrium outcome, they must offer alpha theta 2 after a success, right? If that's not the case, then we will not have an equilibrium outcome. It will not be optimal for Warwick to administer the test because it's incurring a cost in doing so, and the test is not the test is not making any difference to their wage offerings. So in any equilibrium, we must have that after success, you offer a wage which is different to the wage that is offered after a failure, because only then is the test playing the intended screening purpose. So once we've acknowledged this, then we sort of have to calculate Warwick's expected utility from administering the test. So this is basically going to be, so Q, the probability that the candidate is of a low type. So with probability 1 minus P, they fail, right? In which case Warwick will offer alpha theta 1. But with probability P, they succeed, they pass, and Warwick will offer alpha theta 2. Okay. And we're going to need this, right? And so then with probability 1 minus Q, the candidate is of high type, and they always succeed. So Warwick's payoff will always be theta 2 spread alpha theta 2. And then of course Warwick incurs the cost C of administering the test. Okay, so this expression is Warwick's expected utility from administering the test. Warwick's expected utility from not administering the test. Do not. Well, Warwick. Well, of course, this depends on whether Warwick offers alpha theta 1 or alpha theta 2. So if Warwick offers alpha theta 1, then as we've seen above, its expected utility is Q times theta 1 squared alpha theta 1. If Warwick offers alpha theta 2, its expected utility is right. So so the expected utility, Warwick's expected utility from not administering the test is basically going to be the greater of the greater of these two, right? Because as we've seen above, depending on which is greater, right. So yeah, right. So in any equilibrium outcome, whichever is greater will obviously be what Warwick receives. So we have that. Okay, so then to summarize, right, so let's call this 2 and let's call this 1. So Warwick offers the test if basically 1 is greater than equal to 2. And so once you got to this stage, I mean, there really is, no great need to undertake the required algebra. Okay. Okay, part E. Suppose theta is uniformly distributed on 0, 1. What does Warwick offer and how does it depend on alpha? Okay. So the first thing to notice here, okay, so suppose that, okay, suppose we didn't have alpha, right? So we just had, so we had that this is uniformly distributed on 0, 1, and say that it was optimal for Warwick to offer wage equal to theta. Okay, so in this case, Warwick is going to offer, and so say that they could offer any wage, any positive wage, right? Now theta is in 0, 1, so that means that Warwick is not going to offer a wage outside of 0, 1, right? So when Warwick is trying to find the optimal wage, it's going to basically maximize W in 0, 1. And so it's going to maximize its expected utility, right? So it's going to find the optimal wage within 0, 1. And this is basically going to be, the expected utility is going to be the probability that type is less than equal to W times the expectation of theta given theta is less than equal to W, subtract the wage. Okay, and then you're going to basically maximize this with the constraint that W is restricted to the domain 0, 1. Okay, so that's just by way of introduction to this type of problem. But we have that basically it is optimal for Warwick to offer a wage equal to alpha times theta, as we've reasoned above. Now theta times alpha, so theta is distributed of 0, 1. That means theta times alpha is going to be distributed 0 to theta. So Warwick is not going to offer anything outside of 0 to theta. So we basically, what we do is we calculate Warwick's expected utility from offering a wage in 0 alpha, which is going to be the probability that theta is, the probability that, right, so the candidate accepts if theta times alpha is less than equal to the wage times the, so this is, again, we're formulating an expression for Warwick's expected utility from offering some wage in 0 to alpha, which we'll then try to maximize. The probability that the candidate accepts, right, which is this, times Warwick's expected utility, which is the expectation, which is the expectation of theta given. Now this over here implies that theta is less than equal to W over alpha, right? So theta, given that theta is less than equal to W over alpha, subtract W, right? Okay, so we're going to have, so this term over here, you know, from the CDF of the uniform distribution, we have that, so we have W, so this term over here, so we have W subtract 0, right, over alpha subtract 0, so we have W over alpha. Okay, so we have W over alpha, and then we have, so we then calculate this expression. So this is going to be the integral from 0 to W, right? So it is an expectation with an altered the expectation of theta with an altered support. Okay, and we get alpha over w because we want basically 1 over w, right, which is what we can call our, as it were, new PDF. Right, so the PDF times the random variable. Right. Okay. So we have that. Okay. So okay, and then we just want to maximize this expression with respect to w, keeping in mind that w is it is in 0 to alpha. So taking the first order condition with respect to w, okay. So we have a few cases here, right? So notice that if alpha is less than half, then this term, this expression, this expression is always positive, right? So we have no interior solution. So we have something like this, right, over the domain, which means that the optimal wage is alpha. Okay. And notice that trivially, w and then alpha squared is always positive, right? If alpha is greater than half, then this derivative is always negative. So we have something like this, and therefore the optimal wage is 0. And then if alpha is equal to half, then that means then this expression is always 0. So any wage in 0 to alpha is optimal. Okay, and that is that question.